Hi everyone, welcome back to another episode of Phys 4250 or Phys 8250, Design and Applications of Lasers. I'm your instructor, Dr. TJ Hammond. Today we're going to be continuing on for Wednesday, October 7th on laser oscillation, power, and frequency. So why are we covering this? Up to now, so last week what we were covering was discussing intensity or the photon flux inside of a laser cavity. Now we actually want to try and extract this energy, extract these photons out of the cavity and actually shine them onto something. So, like a laser pointer or something like that. So chapter 5 talks about the output power and how to select a certain frequency. So on Monday, we talked about using the uniform field approximation to optimize the output coupling. Today's lecture, we're going to be covering sections 5.9 to 5.11, which discuss frequency pulling, single mode oscillation, and the line width. So we'll be discussing what modes are and how those are related to frequencies. And so there's actually no daily assignment this day. All right. So we have what are called cavity modes. All right. So when we have an electromagnetic wave resonant inside a laser, it should be noted that in order for these mirrors to provide feedback, then that means that these waves have to constructively interfere with themselves as they oscillate back and forth. In order for them to constructively interfere, the only way for that to happen is actually if there is no field at the surface of this mirror. Okay, so it's the same thing if you've taken quantum mechanics and you've looked at particle in a box. It's the same solution. So what you have is some kind of sine curve where at z equals 0, you have the sine of this phase is 0, and then you quantize this field by the fact that the sine at k 2 pi, which is 2 pi over the lambda, times the length is also going to have to be 0. So this quantization ends up allowing for this to be resonant, and that defines these modes. And so this wavelength can be whatever this length of this cavity is times 2, because this thing goes to the right and then it comes back to the left. So the total cavity length is actually 2 times the length of the cavity, divided by m, where m is this mode number. And so that means that the frequency of this mode that's oscillating in this cavity or that's resonant in this cavity is going to be m times the speed of light divided by 2 times the cavity length. So that's what, when we talk about modes, these modes are the frequency that are resonant within the cavity. So lasers can't put out any color that's like within the gain bandwidth of our gain medium. It has to be, it's kind of quantized based on the resonance of this cavity. Now, of course, we don't just have bare cavities, we actually also have some kind of gain medium in there. And so if this medium happens to be a length little l, where the cavity length is big L, then this index of refraction changes that wavelength, right? And so this wavelength doesn't have to be resonant within the crystal, but it does still have to be resonant within this entire cavity. And so this index of refraction changes the wavelength inside the gain medium. And so now that means that this resonant mode is slightly modified by taking into account the length of this gain medium with an index of refraction at this frequency nu of m for the mode number m. Okay. So what this means is our cavity modes are actually quantized, and we'll discuss this when we get to what the gain looks like in this case. Now, it's not. Now the thing is that it's not perfectly quantized, and that's because there's actually a line width to the cavity. So when we have the rate of the photon rate equation is given by some gain. So we add photons to the cavity, by the gain, and we lose photons from the cavity due to losses. Now, instead of having the gain, what if we what if we suddenly turned off the amount of gain, or what if we immediately pulled out this crystal? Somehow we could do this instantaneously fast. Then we'd have some, intensity in this cavity, and then all that would be left would be the losses. So the solution to this differential equation is, of course, this decaying exponential. Now, this decaying exponential is what the photons are doing, or what the intensity is doing, but it's not what the field is doing. The field is, of course, the square root, or proportional to the square root of the intensity. So that means that the amount that the field is decaying is going to be at half that rate. So we're going to have, instead of C over 2L and then 1 minus R1, R2, we're going to have C over 4L, 1 minus R1 times R2. Now, the field, of course, has to oscillate at some frequency, but we've said that this frequency is going to be, let's just say that it's a bare cavity. This frequency is going to be, some mode number times C over 2L, or when it's the angular frequency, will be this times 2 pi. So what we get is that the field has this exponential decay envelope, and then this carrier frequency, which is the actual frequency that this thing is oscillating at in time. So that's going to be that mode number. And so that means that the field is decaying as e to the minus t over tau, e to the minus I omega mt, where 1 over tau is c over 4L, 1 minus R1 times R2, where that's given, that's this decay rate, or half of this decay rate. Okay, well, so what does that mean? Now that we're all experts on Fourier transforms, we have this field that's decaying at this exponential rate with some carrier frequency omega m. So we can take a Fourier transform of that. So that means that the Fourier transform of this is going to be 1 over tau plus I times omega minus omega m, where omega m is that mode frequency. So it means that the spectrum is going to be 1 over delta omega squared over 4 plus omega minus omega m squared, where delta omega is this full width half max line width that I got you guys to calculate in the first assignment, which is going to be 2 over tau. But 2 over tau is c over 2L, 1 minus R1 times R2. But that's exactly what we had here for this amount of loss, right? So this line width then is just going to be proportional to how long photons stay in the cavity, right? So that's exactly what this is saying, is that we're going to have some full width half max line width that is going to be a characteristic of how long photons stay in our cavity. And how people, what would people refer to, or how people refer to this is called the quality factor. And this quality factor is Q, which is omega m, this optical frequency of this mode, divided by the bandwidth of this resonator. So an optical frequency is on the order of 10 to the 15, where the bandwidth of a resonator can be on the order of megahertz or even kilohertz or even single hertz. So say it's 10 to the 3 for a kilohertz. That means the quality factor for an optical like resonator for a laser is going to be on the order of 10 to the 12 or something like that. So it's a really high quality factor. We'll be talking about this Q later on when we talk about amplified pulses. So remember what the Q stands for. It's for the quality factor of the cavity. Okay, so let's visualize this. So as we said, there's going to be this bandwidth of this cavity mode. And so as you can see here, I've plotted this in Python, and this is really, really small. So this is on the order of, we have this optical mode, which is something like 2 times 10 to the 15. And then this is on the order of gigahertz here, so 10 to the 9. So this is a few gigahertz that this is spanning, but the optical mode is in the order of petahertz, so 10 to the 15. So we have this mode is centered at omega m, our optical mode, and the bandwidth delta omega, which is, as I said, given by the lifetime of the photon in the cavity. So this is when we have a cavity length of 10 centimeters and the R1 times R2 is 0.9 or 90% reflective mirrors. and the essential wavelength is 1 micron. Now, how do we obtain a single mode? So if you think about it, we have all these modes are going to be given by Cm over 2L for these frequencies. So the separation of each of these modes is going to be C over 2L. So that is going to be given by the repetition frequency of the laser. Or you can think about that C being the speed of light of the photons and 2L being the total cavity length. So this is a velocity over a distance. And so that is saying, I guess in a bare cavity, how long it takes for a photon from here to go all the way to here and then back to here. And so that's given by that C over 2L. So it's called the repetition rate of the laser, or the mode spacing of the laser. Now, your gain profile can have some bandwidth. So the gain profile, remember, is given by the absorption cross-section. So absorption cross-section is exactly what it sounds like, that it's going to be some frequency-dependent thing. So if you have something that absorbs over a very broad bandwidth, so it absorbs a whole bunch of different frequencies of light, then this gain profile can be very, very broad. And by very broad, I mean this could be from, like, say, green all the way through to orange or something like that. So this could be very, very broad and spans many, many, many modes. So that means that we could have gain that spans all these modes, and the laser could be resonant with any of these modes at any time. And so that means that at any instant in time, the laser could be hopping from one of these modes. So we could be, resonant with this mode, and then it'll hop and then have gain here and be resonant with this mode. And when it hops from one mode to another, it turns out the phase can be random because they're not necessarily linked together. And so this is called mode hopping, which is something you actually can see in lasers, not in general, you see this as general pen lasers and stuff like that, but it takes a sensitive measurement to actually see that these modes are actually hopping, because often these modes aren't very well separated. Now, something happens that's kind of surprising, that maybe if you've been thinking about this, you'd kind of expect this to happen, but you probably weren't expecting this, that of course at steady state, our gain is going to be the threshold gain, right? So if the gain is always going to be the threshold gain, that means that the gain equals the losses of the cavity, right? And so what that means is that there's always going to be some maximum of the gain profile that is that is going to be maximized, and all the other part of the spectrum is going to have modes that doesn't have as much gain. So what that means is that, for example here, this mode here will be resonant and well amplified, but this here, right, this mode here is going to be below the threshold gain. And if it's below the threshold gain, then that means that photons here aren't being amplified enough in order to reach steady state, and those modes actually die off. So as soon as we're at steady state in our laser, then it means that our gain is at the threshold gain, which means only one mode is actually going to be our laser mode. I'll have an aside because this is mentioned in your textbook, so if you guys are actually reading through your textbook, or if you go into grad school and deal with lasers, this might be something that's brought up, which is inhomogeneous broadening of the gain medium. If you have something that's inhomogeneous broadening, so this would be, say, in a gas laser, so in a helium neon laser, for example, the gas molecules will be going around with some velocity that's dependent on their temperature. That Doppler broadening, because you have some atoms going to the left and some atoms going to the right, their resonant frequency will be slightly shifted because of their velocities, and that's called Doppler broadening. That's an inhomogeneous broadening, and it actually means that some of the gain can actually be slightly above threshold. I just thought I'd mention that because on the off chance that somebody says that if you go into grad school and you end up actually working with lasers, it would be something that probably comes up. Okay. Now, this This picture here is if the modes are actually still fairly well separated compared to the gain medium, but that's actually sometimes not the case. Sometimes you have this mode spacing is extremely short. So as we've had here, C over 2L, where L could actually be very long. It could be several meters. I've worked with lasers that are about 10 meters long. I've also worked with lasers that are just a few millimeters long. But if this laser cavity is 10 meters long, then this mode spacing here is actually quite short. It can be on the order of 10 megahertz. And so that means that this gain profile is going to be extremely broad compared to these modes. And so even when you have, you have this gain at threshold, there are so many modes that are under this gain profile, you can still have this mode hopping. And so when you have this mode hopping from, you have gain here, and then you have gain here, and then you have gain here, even this one may have some gain or something like that, it's hopping between all these modes. You end up having like an unstable laser is basically what happens, and you don't want to have that. One of the reasons why lasers are good is because they can be extremely stable. So what you can do is you can like pre-select the frequencies that are coming out, and you can do that with what's called a Fabry-Perot etalon. So for those of you who have taken 3210, we end up dealing with Fabry-Perot etalons. But if you haven't seen these before, it's basically just a piece of glass with two fairly highly reflecting surfaces. And you stick this inside the cavity, and the index of refraction of this Fabry-Perot etalon and then the length of this Fabry-Perot etalon only allows for some resonant mode. So you make this exactly some length. So say, it's exactly a certain number of wavelengths, and then that means that only that wavelength can oscillate within this etalon. And so by forcing it to only oscillate within this etalon, it also forces the entire cavity to only oscillate at that frequency. So maybe visualizing it in terms of the spectrum is a little bit more straightforward, in that we have this really broad gain profile. We have all these very tight modes close together because of the cavity length being very long. And then we have a really short length of this Fabry-Perot etalon. So maybe this is a few millimeters long. And then that means that the mode spacing of this etalon becomes very, very broad. And so that means that now you can only have this single mode being resonant within this laser cavity, because it's the only mode that's resonant within this etalon. And this is how you can make a laser oscillate at only one frequency. So that's it for this lecture. We'll be discussing a little bit more about the actual derivation of how the Fabry-Perot etalon works on Friday. And that is it for this lecture.